Ladies and gentlemen, welcome to this short video. In this video, I'm going to solve problem 41 from chapter 10. There are several ways to solve this problem. I'm going to talk about the way that makes most sense to me. With that, friends, let's get started. In this problem, you can see that we have two rods and two masses. I chose to look at this as four particles: rod 1, mass 1, rod 2, mass 2. And I want to find the rotational inertia of each of my four particles, and then I just add up those four particles to get the rotational inertia of the system. The rotational inertia of rod 1 is equal to 1/3 ml squared. We know that because we know the rotational inertia about a rod through its end point. And rod 1's rotational point is right there, so I can just use that formula. And I got 0.00125. That would be in kilogram meter squared. The rotational inertia of mass 1 is just mr squared. All point masses are mr squared. The mass is 0.85. The distance, r, is the distance from the center of mass to the point of rotation. In this problem, that's 0.056 meters. Yeah, and I see that I miss. That should be 0.056. I just missed a zero earlier. But I'm pretty sure my number is still valid. And when I do this, I got 0.00267. The rotational inertia of rod 2. Rod 2 is out here. The pivot point is way over there. So how I'm going to deal with this is use the parallel axis theorem. The parallel axis theorem says the rotational inertia of that object is equal to the rotational inertia about its center of mass plus some offset value. I know the rotational inertia of the center of mass is equal to 1/12 md squared plus some offset value. And the offset value is going to be mh squared, where h is the distance from the center of mass to the point of rotation. From the center of mass to the point of rotation, this distance is h. So my h is going to be 1.5 d. It's 1.5 d, and I have to square it. So parallel axis theorem, the rotational inertia about the center of mass plus the offset value, mh squared, where h is the distance from the center of mass to the point of rotation. In this case, it's 1.5 h. And when I put all those numbers in, I got 0.00875. The last thing that I need to find is the rotational inertia of the second mass that's hanging out on the end. There's my mass. There's r. So r is going to be 2d in this case. And I got 0.01066. Putting all of that together, I got the rotational inertia of my object, the rotational inertia of rod 1, mass 1, rod 2, mass 2. Add up all those values, and I got a rotational inertia of the system. Units would be kilogram meters squared. Part B asks me to find the kinetic energy. All right, well, the kinetic energy is just 1/2 I omega squared. I got 0.0011 joules. I said at the outset that there are several ways to solve this problem. One of the other ways you could have looked at this problem is to take in the entire rod as one rod of length 2d and found the rotational inertia of the whole rod to be 1/3 ml squared, where m would be the two masses added together and L would be 2d. And you'd get the same thing. Then you would have the rod, one long rod, and 2 point masses that you could add together. That's the other way that you could have solved this problem. So there you have it. In this video, we saw how we can take four objects, in this case, rod 1, mass 1, rod 2, mass 2, and add them together to find the rotational inertia of the system. And then we can find all of our other quantities, such as the kinetic energy, based off that rotational inertia. That's all for this episode. We'll see you in the next one.